Number 24. Okay. Samuel is investigating the movement and forces in tall buildings. Woohoo. Skyscrapers have got lifts or elevators to transport people up and down. Look at the speed time graph for part of the journey of a lift up a skyscraper. So it's 36 seconds worth altogether. Okay, the lift travels 30 meters before it reaches cruising speed. So up to this point, so it says at point X. So up to this point, it has travelled 30 meters. Okay, Samuel thinks that the cruising speed is 5 meters per second. Use a calculation to explain if he's correct. Now, the simple idea is, it's gone 30 meters in 6 seconds, so it's 30 divided by 6, which is 5 meters per second. And yes, that's its average speed. But it's not going at its average speed all the time. It starts off at 0 and it ends up at whatever this cruising speed is. Okay, so whatever that is, we'll call that V. Okay, so we have to say what's the distance that it's travelled, bearing in mind it started at 0 and it ended up at V, and it did 6 seconds worth of travelling. Now, it's a speed time graph. The distance travelled by an object is the area underneath a speed time graph. So if I shade in the bit up to 6 seconds, which is X, that is the distance it travelled during that time, and that must be 30 meters. So that means if we work out what the area of that triangle is, it has to be 30 meters. Well, the area of that triangle, based on the graph, is half the base times the height, which is half times 6 times, well, the height here is V. So which is half of 6 is 3, so it's 3 times V. So 3 times V is 30 meters. So V must be 10, so it's 3 seconds times V. So it's 10 and it's meters per second. So 10 meters per second is the cruising speed. And if we think about it now, it starts at 0, it ends up at 10, its average speed was 5, which is in the middle. And so yes, its average speed, 30 meters in 6 seconds, is 5 meters a second, but its cruising speed, the top speed, is 10 meters per second. So how does this compare to what Samuel thinks? It is twice the size, or twice as big, so Samuel is wrong. Okay, let's see what the next part is. Okay, the lift begins to slow down at point Y on the graph. There's point Y, there's point Y. Okay, compare the acceleration between 0 and X with the acceleration between Y and Z. Okay, another thing you need to remember for speed time graphs is how you find the acceleration. Now, acceleration is the change in velocity, really, divided by the time it takes. And that means that it's the change in velocity, which is in this case the change in speed, because it's always going in a straight line. Change in speed divided by the time. That's the slope, the gradient of this line. So the gradient of this line is the acceleration. The gradient of this line is the deceleration. And that's one obvious difference. This one it's speeding up. This one it is slowing down. This one it takes 6 seconds to change speed up to 10. This one takes just 2 seconds. Okay, so that's 2 seconds from 34 to 36. It takes 2 seconds to slow down from 10 meters a second to 0. Okay, so here the deceleration is the change in velocity, which is 10, divided by 2, which is 5 meters per second squared. Here the acceleration is the change in velocity from 0 to 10, so that's 10, divided by the time, which is 6. So that is 10 divided by 6. Let's do that. I can't do that in my head. 10, well, I can do it in my head, but I'm not going to. 10 divided by 6 is 1.67. So 1.67 meters per second squared. Okay, so between 0 and x, it's accelerating at this. Between y and z, it's accelerating, or it's decelerating at this. So let's put those down. Okay. Between O, x, it accelerates at 1.67 meters per second squared. Between y and z, it decelerates at 5 meters per second squared, i.e. about 3 times as much, about 3 times the rate. 3 times the rate of acceleration. Okay. We could also mention another thing, which is the fact that it takes a longer time. It takes 3 times as long to build up speed as it takes to reduce speed. But that effectively is why it has a different deceleration, because it starts and finishes at the same change of velocity, but at just a different time. Okay, when the lift is moving at its cruising speed, work is done by the motor pulling the lift. Now you have to remember, work done is force times distance in the direction of the force. So that's a thing to remember for starters. Okay, there are 8 people in the lift. The average weight of each person is 600 newtons. So let's just quickly put that down. So total is 8 times 600, which is 8 times 600 is 4,800 newtons. So that's the people. That's the people. The weight of the lift is 6,000 newtons. So the total of everything is 6,000 plus 4,800, which is 6,000 plus 4,800, which is 10800 newtons. Right. Calculate the power needed to move the lift and the 8 people at cruising speed. Okay, so we need to know firstly the energy transferred. So power is energy divided by time. Okay, and the energy is the amount of work done. So it's the work done divided by time. And that is the force times the distance divided by the time. Now, being very sneaky about this, we can also say that this is the force times the distance divided by the time, which is the speed that it's going. It's going at its cruising speed, so it's going at the same speed all the time. So its speed is distance over time, and if we multiply that by the force, we'll get the work done. The power. But let's do it the sort of fairly straightforward way. Okay, we need the force times the distance. How far does it travel? So the distance that the lift goes is, well, it's going at 10 meters a second. Okay, that's 10 meters a second. We worked that out earlier. And it's going from 6 up to 34. So the time that it's at cruising speed is 34 take 6. Whoops. 34 take 6, which is 28 seconds. Okay, so it's going at 10 meters a second for 28 seconds. Okay, distance. Speed is distance over time, so distance is speed times time. Okay, so the distance is speed, which is 10, times the time, which is 28, which is 280 meters. That's how far it goes up the skyscraper at its cruising speed. Okay, so the work, which is force times distance, is, well, it's 10800, that's the force. It's the total weight of all the objects, the lift and the people, times 280 meters. Okay, which is, okay, 10800 times 280, which is 3024000, and it's work, so it's got to be joules. Now I need to find the power, is the work done divided by the time, which is this number, 3024000, divided by the time that it took. Well, how long did we say it took? 28 seconds. So we divide that by 28. Okay, and we get, so that's our number divided by 28, 108,000. And that is power, so it's in watts. So our answer is 108,000 watts. So going back to what I said over here, If I just done the force times the speed, so force times its speed, v, I'd have 10800 times the speed, which was 10, which would add another naught on the end, and I would get this number. So this is a way of doing it, but if you don't know that, you can slog all the way through, and actually it works out exactly the same. So you have to firstly calculate the work done, the force times the distance. For that, you need the distance, which you need speed times time. That gives you the work done. Then you need the power, which is work divided by time. So you divide that number by the time, and you get 108,000 watts. Okay, last part. Calculate the total mass of the lift and the people in it. Well, they've given us the weight. So weight is mass times gravity. That's another equation you have to remember. So mass is weight divided by gravity. If I put this into a triangle, I've got m times g at the bottom, w at the top. Okay, so mass is weight divided by gravity. So that is, where are we? 10800 newtons, because that's the lift and all the people in it, divided by g, which is 9.8. They've given us 9.8 rather than 10. If you had to use it and they didn't give anything, then you'd normally use 10. But we're going to use 9.8 this time. So 10800 divided by 9.8 is, okay, which is 1102.0408. And that's going to be the mass, because that's what we're calculating. So that's going to be kilograms, because that's the unit for mass. Okay, so that's our answer, but give your answer to two significant figures. So we have to give this to two significant figures. So basically it's 1,100, and then we ignore all the other digits. So it is 1,100 kilograms.